Till now we are aware that diamagnetic material opposes the magnetic field, paramagnetic materials favor the magnetic field, ferromagnetic materials favor the magnetic field. But there is a difference. As soon as you remove the magnetic field, diamagnetic materials again come in their original state. Paramagnetic materials again come in their original state. That means their electrons are now again in random direction. But what happens in case of ferromagnetic material when the field is removed? So this is important. In some ferromagnetic materials, the magnetization persists. That means it remains. Even if you remove, the magnetization remains. This is the method of making permanent magnets. Otherwise, how can you make permanent magnets if the magnetization is removed? Such materials are called hard magnetic materials. These materials are called hard magnetic materials. Suppose we have a material which is ferromagnetic. We put in this external magnetic field B naught, and then after putting it there for some time, their internal magnetic moments are aligned, and now we remove this external magnetic field. Still this is magnetized. Then these materials are called hard magnetic materials or hard ferromagnets because they can retain their magnetization. Now another case is that again these materials are ferromagnets. We put in external magnetic field, again they align in this external magnetic field. Now we remove this external magnetic field. So what will happen? Their internal magnetization is also disappeared. So there is no magnetization. So these are called soft magnetic materials. These are called soft. But what? So now you would ask, what is the difference between soft magnetic material and paramagnetic material? Because in paramagnet it also becomes magnetized, and as soon as you remove the magnetic field, it again becomes paramagnet. So only difference is that the paramagnet is from 1 to this goes 1.0001, so very less. Again, even if you take soft ferromagnet, this number 1 goes to very high, like 400 or 500 times. So this number is very high. Though you remove the external field, this again comes back to its original state, but this number of magnetization is quite high. This magnetic field associated is very high. So that is the difference between soft magnetic material and paramagnetic material. And which materials retain their magnetization are called hard magnetic materials or hard ferromagnets. Such materials form permanent magnets. So we know permanent magnets we always use, like compass needle. So those needles are formed because of these hard ferromagnets. The materials which magnetization disappears on the removal of external field are called soft ferromagnetic materials. Soft ferromagnetic materials. Soft iron is one of such material. So if we take soft iron, so soft iron is soft ferromagnetic material. That means if you remove the field, it will again become non-magnetized. Now what was the difference? The relative magnetic permeability is very high. Appropriately enough, there are a number of elements which are ferromagnetic. So there are many elements which are ferromagnetic: iron, cobalt, nickel, gadolinium, and etc. The relative magnetic permeability is greater than 1000. That means mu r is very large, greater than 1000. Mu r is very high for these materials. Again, a paramagnetic material is not a ferromagnetic, even though a soft ferromagnetic material, though as soon as you remove the field, will become non-magnetized, but the magnetization in the field is much higher than a paramagnetic material because there are domains. The ferromagnetic property depends on temperature. Again, it also depends on temperature. At high enough temperature, a ferromagnet becomes a paramagnet. So at very high temperature what happens? A ferromagnet also becomes a paramagnet. Why? Because the domains starts breaking, because there is enough energy to break those domains. So that domains starts breaking at high temperature. So what will happen? This ferromagnet becomes paramagnet. At high temperature, the domain structure disintegrates. That means it starts disappearing with temperature. At high temperature, there are no domains. The disappearance of magnetization with temperature is gradual. That means it is slow, not immediate. It is a phase transition reminding us of a melting of a solid crystal. So this is very similar as the solid melts. Some solid converts into liquid. Similarly, this transition take place slowly. The domains will disintegrate and there is no magnetization. The temperature of transition from ferromagnetic to paramagnetic is called Curie temperature. This is another thing, that suppose below this temperature, let us say one temperature, this cobalt. For cobalt this is 1394, again this is in Kelvin, this is not centigrade. Below this temperature cobalt is ferromagnet and above this paramagnet. So what is this difference between ferromagnet and paramagnet? For ferromagnetic materials the magnetization is very high. The magnetization is very high because permeability is very high, more than 1000. For paramagnet it is higher than 1 but not very high, let us say 1.0001. So definitely this is much less powerful than a ferromagnet. And what is the temperature at which this transition take place? Ferromagnet becomes paramagnet. This is called Curie temperature. Now table 5.4, this table lists the Curie temperature of certain ferromagnets. So in this table temperature of some of the ferromagnetic material is given. The susceptibility above the Curie temperature, again see, this is above the Curie temperature, that is in paramagnetic phase. That is in paramagnetic phase. What will happen in paramagnetic phase? Chi is equal to C upon T minus Tc. C upon T minus Tc, where C is Curie constant, Tc is that critical temperature or Curie temperature, and T is your temperature. T is the temperature in which that material is there. Tc is Curie temperature and this C is Curie constant. And again this is in paramagnetic phase. That means this T must be greater than Tc. T must be greater than Tc. So this law is only valid above the Curie temperature. That means this temperature must be higher than Curie temperature. So let us see these materials. What are these materials? Cobalt 1394 Kelvin. Again this is Kelvin. So around 1100 Celsius. Iron 1043, that means around 750 Celsius. So these temperatures are very high. Ferrous oxide, that is 893 Kelvin. Again excuse me for my pronunciation of this ferrous or ferric oxide because I am not very aware about chemistry. So this might be ferric oxide. This is ferric oxide. Nickel is 631 Kelvin. Gadolinium is 317 Kelvin. So if you convert this into Celsius, so what you have? You have around 44 degrees Celsius. So very less. So even if little bit temperature is given to gadolinium, this will convert into paramagnetic substance from ferromagnetic. Now very simple exercise for you. Take a magnet, just heat it with the help of something, a tongue kind of structure on the gas, and you will find that once it is heated it will no longer be magnetic. So the magnetic properties are lost with temperature. So let us read this question, example 5.11. A domain in ferromagnetic iron is in the form of a cube of side length 1 micrometer. So domains are there, domains are cubic, and what is the length? 1 micrometer. Estimate the number of iron atoms in domain. So we have to estimate the iron atoms in that domain and the maximum possible dipole moment. And again, let us assume that all the atoms are giving dipole moment and that is aligned in same direction. So maximum possible dipole moment we have to calculate, and magnetization of the domain. So how do we calculate magnetization? Magnetization is equal to, first we will calculate m net, so that we calculate maximum and we divide by the volume of one domain. So that will give us the magnetization. The molecular mass of iron is 55 gram per mole. So this is molar mass, and its density is 7.9 gram per centimeter cube. So density is also given. Assume that each iron atom has a dipole moment 9.27 into 10 to power minus 24 ampere meter square. So we know the density, we know the molar mass. So we can first calculate the how many atoms are there in this, and each atom is contributing this much. So we simply multiply it by number of atoms. So using that we will get the m net for a domain, then we will divide that with the volume of domain. What we get? Magnetization.